Welcome. In this video, we're going to talk about the one-way ANOVA. The analysis of variance ANOVA, it provides a method for comparing several population means, that is the means of a single random variable, for several populations. Now I'll be focusing on the one-way ANOVA. Now this is the simplest of the ANOVAs, and this type of ANOVA is called a one-way analysis of variance because it compares the means of a variable for populations that result from classification by one other variable called the factor, and the possible value of the factors are referred to as levels of the factor. So things like you could look at the growth of a plant for different levels of fertilizer, and you could look at the mean growth and see if certain levels of the fertilizer or different fertilizers produce greater growth. That type of idea. Now the one-way analysis of variance is the generalization to more than two populations of the pooled T procedure. Now that is, both procedures will give us the same results when applied to two populations. But with the ANOVA, we generally have more than two populations. So we have to talk about what assumptions must be met in order to even do an ANOVA problem. Well, the assumptions are conditions for the one-way ANOVA. From each of the different populations, the sample must be taken by a simple random sample. That's number one. Number two, independent samples. The samples taken from the populations under consideration are independent of one another. And that there are normal populations. For each population, the variable under consideration is normally distributed. So we have different ways that we can do this. We could look at probability plots and box plots for each of the different samples, but sometimes the sample sizes are small, so we do a residual analysis. And that is, a residual of an observation is the difference between that observation and the mean of the sample containing it. So for each sample, take that observation minus the sample mean. Make a probability plot of all these differences, and if it's relatively linear, you can assume normality for the different populations. Now the ANOVA is robust to moderate violations of normality, and also this last assumption, equal standard deviations. The standard deviations of the variable under consideration are the same for all populations, and we have a rule of thumb to go by, that the largest sample standard deviation can be no more than twice the smaller standard deviation. So the largest standard deviation must be less than 2 times the smallest standard deviation, or their ratio is less than 2. Now if these are met, we can do the ANOVA. So let's see, what's the logic behind a one-way ANOVA? Well, the reason for the word variance in analysis of variance is that the procedure for comparing the mean analyzes the variation in the sample data. So we're going to look at two examples. So I have a sample from population 1 and a sample from population 2. And I'm going to look at their means, and you can see that they're different. But let's actually look at the data in this dot plot below. As you can see, for both population 1 and 2, there's a lot of variation in the data. So we're not clear whether the difference in the mean is due to the difference between population mean or to the variation within the populations. So now let's look at a second example. I have population 1 and population 2. Now their means are different, but look at the dot plot. We can infer that the population means are different because it seems more plausible that the difference between the sample means is due to actual differences in the population, not to the variation within each of the populations. So there are some basic ideas behind the one-way ANOVA. We're going to take these independent, simple random samples from the populations. We're going to compute the sample means. Then we're going to see if the variation among the sample means is large relative to the variation within the samples. So now we're going to talk about some quantitative measures of the variation among the sample means and the variation within the samples. Then we're going to need an objective method for deciding whether the variation among the sample means is large relative to the variation within the samples. So we're going to talk about something called the mean square error of the treatment, the MSTR. It measures the variation among the sample means. And then the mean square of the error, MSE. It measures the variation within the sample. Then we're going to compute the ratio of these two. It's the F statistic. It compares the variation among the sample means to the variation within the sample. Large values of F indicate that the variation among the sample means is large relative to the variation within the samples, and hence that a hypothesis of equal population means should be rejected. So now we're going to take a look at some notation, and different books use different letters and notation. The book we use, they use I for the number of number of populations, and that uppercase I can sometimes look like a 1, so I actually don't like that. Generally, most books use K, some books use L, but I think K is very distinguishable from numbers. And then I'm going to use an I. It's going to be the number of observation in each sample. Our book uses J, but that can be mixed up with indices when we're doing summations. That's why I'm going to use N. So then we can look at the individual sample means. X, I dot with a bar over it. That means my index I is going to go from 1 to K, the number of populations that I have. And it's just you calculate the mean of each of the individual sample. So the sample variances for the individual samples, and then the grand mean where you add up all the X values for all your different treatments, divide by total number of data values to get what we call the grand mean, and then the grand total of observations. Now we're ready to see the mean square and the F statistic in the one-way ANOVA. Now the mean square of the treatment is the sum of the square of the treatments divided by the number of treatments that you have minus 1. So the mean squared error is the sum of the square of the treatments divided by K minus 1, remembering that K is the number of populations or treatments. Now, the sum of the square of the treatments is N1 times X from you're going to look at your sample mean for population 1 and subtract it from the grand mean and square it and multiply it by that sample size for sample 1, and you add up for all the different populations the same quantity. Then you divide it by the K minus 1 to get the mean square of the treatment. Now many problems we try to have the same sample size. So many of the problems in class we will, but our first example will have different. But if it is the same sample size, then the calculation is simplified a bit by just pulling out that same sample size. Now looking at the mean square of the treatment, remember that that measures the variation among the sample means. So now it's time to look at the mean square of the error, which measures the variation within sample, just the natural variation. And that would be the sum of the squares of the error divided by the total number that's in all the populations minus how many different populations you have. Well, how do we calculate the sum of the square of the errors? Well, we take each sample's variation, multiply it by the sample size of that sample minus 1. And we do that for each of the different samples that came from each of the different populations. So then we have that calculation for the mean square of the errors. And then the simplified calculation if the sample sizes are all the same. Now once we have those two quantities, we now can calculate our test statistic called the F statistic. That would be that ratio of the mean square of the treatments and the mean square of the error. So we just divide the two and we get our F statistic. So It compares that variation among the sample means to the variation within the sample means. So, this distribution of the F statistic for the one-way ANOVA, we have to know that in order for us to calculate p-values or to use critical values in order to quantitatively reject or not reject the null hypothesis. So the F distribution for this one-way ANOVA with the conditions that are all met above will have degree of freedom of k minus 1 and n minus k if the null hypothesis of equal populations is true. So with all these calculations or formulas, we now have all the components that are required to formulate a procedure. But there's something that we would want to cover before, some additional concepts that will help us in the one-way ANOVA procedure. We're going to talk about the one-way ANOVA identity and the one-way ANOVA tables. Now the one-way ANOVA identity is that the sum of the square total equals the sum of the square due to treatment and the sum of the square of the errors. Now this sum of squares of total is the total variation among all the samples. And look at what that exactly is. It's our total variation among all the observations. It can be partitioned into these two components. The sum of the square of the treatments, that error due to being in the treatment or population that you're in, and the other is the sum of the square of the errors, the error in the system that can't be changed. Now if you wanted to calculate the sum of square total, you take each of your data values minus that grand mean and square it, and then you do that for each of the different populations. All the different variables in there. When we refer to xi like this is where we're talking about each variable in all the populations you subtract from the grand total and you square those differences. That's the sum of the square of the total. Now we're going to talk about the one-way ANOVA table. It's used to organize and summarize the quantities that are required for performing a one-way ANOVA analysis of variance. So in this table, you're going to have the source of your error, which would be the source of the variation, which would be from your treatment and your error. And remember, adding those two will give us the total. The degrees of freedom for your treatment are k minus 1, the number of populations minus 1. The error is your total number that's in all your populations, all your data values, minus the number of populations. So the total should be, the degree of freedom for the total should just be adding up those two degrees of freedom, and then you would get n minus 1. Now you will calculate your sum of the squares for the treatment, for the error, and for the total. From that, we now can calculate the mean square of the treatment. We would just do the ratio of the sum of the squares and the degree of freedom. So the mean square of the treatment is the sum of the square of the treatment divided by k minus 1. The sum of the square of the error, we do the ratio of the sum of the square, the mean square error rather, is the sum of the square of the error ratio with n minus k. So we take s, the sum of the square of the error, and divide it by n minus k. And our F statistic is now the ratio of that mean square of the treatment and the mean square of the error. So we'd have to fill in this chart in order to calculate our test statistic called the F statistic. And here are the calculations, the summary of the calculations. We have the defining formulas, but sometimes when we have our data, there's the computational forms of the formulas that make it easier to do the calculations. So now it's time to get into the nitty-gritty of the one-way ANOVA test. The purpose of this test is to perform a hypothesis test to compare K population means, mu1, mu2, all the way to mu k. Now, assumptions that have to be met, as we said, simple random sample, independent samples, normal population, and equal population standard deviations. So step 1, state your null and alternative hypothesis. Well, the null is we assume all the means are equal. The alternative is not all the means are equal, at least 2 are not equal. Step 2, state the significance level, alpha. That is, decide on an alpha. Step 3, calculate the test statistic. That is where we're going to use our ANOVA table and get our test statistic, our F statistic. So remember, it's that ratio of the mean square of the treatment divided by the mean square of the error, that F statistic. Now, we have to determine the quantifying values needed to reject or not reject the null hypothesis. So, the p-value approach, and in an ANOVA, it's always a right-tailed test, so we're always looking in the right tail. If we're going to do the p-value approach, we have to find from our F statistic with degree of freedom, k minus 1, nk, we have to use either the back of our book table or use technology to find the p-value. So we want to find that darkened blue area that's to the right of our test statistic. Now in the book, we're going to have to capture that p-value more than likely because we're not going to see the actual test statistic usually in the table. So we'll have to capture it between two values. Or we could use technology and get the exact p-value. Now the classical approach, or finding the critical value, you would look for your critical value, f sub alpha with degree of freedom k minus 1, nk, n minus k, and use the table in the back of the book to find that critical value. Now we know. So remember how we determine whether we reject or do not reject the null hypothesis, which is step 5. In the p-value approach, if my p-value is less than my significance level, alpha, I reject the null hypothesis. Otherwise, you do not reject the null. And with the classical or critical value approach, if my test statistic is greater than my critical value, I'm going to reject the null hypothesis. Otherwise, do not reject, because as I said, all ANOVAs are right-tailed. Once you decide whether you reject or do not reject based on your sample, if there's enough evidence or not, then step 6 would be to state your conclusion in the context of the problem. So this is how we do a one-way ANOVA. In the next video that I'm going to make, we're going to go through an example of an one-way ANOVA problem. Thanks so much for watching.